again. So if you can all sit down with your beers, and we're gonna welcome on stage Daniel Angerhausen, who is the president of Astronomy on Tap Bern. Please. And you can call him Dangerous Daniel for the night.
Merci. Probably loud enough anyway. Okay, so yeah. Hi everyone. So I'm here pretty short notice, so I came up with that talk on pretty short notice, and it had to have Apollo in it. So I already put the moon in the first slide. Anyone can have a guess where the moon is in this slide? Where's the moon here? Do you see this dark shadow going over the Earth? What's that, like a black hole? Or like a swarm of bees or something? No, this is a solar eclipse observed from a geostationary orbit. This is real data taken from orbit, and this is how a solar eclipse looks from space. Okay, so a little bit introduction of myself. So I'm a fellow at the University of Bern, Switzerland, and I'm an astrophysicist, astrobiologist, and I'm also running a science communication startup called Explainables. So we help other nerds to get cooler and communicate better. I also have a couple of handles if you want to add me on Instagram or Twitter or swipe me on Tinder. So a little explanation about myself. So I'm quite a nomad. So for those of you here who are maybe interested in a scientific career, this is maybe a warning for you. So if you want to stay in academia, you have to be mobile. So for me it was extremely crazy. So I started in Germany, then went to the US for part of my PhD, went back, finished my PhD, went to my first postdoc, second postdoc to New York, third postdoc at NASA in Washington DC, and now I'm back in Europe, back in the civilized world, and at the University of Bern. So word of warning, I mean it's an awesome life, but it has its trade-off. So in case you're contemplating about an academic career, I can give you some tips about that. Okay, so let's talk astrobiology. So whenever I start giving a talk about astrobiology, I start with this story about the blind man and the elephant. Does anyone know this story? Anyone heard this story? Okay, so some of you know the story. So the story goes, a couple of blind men find an elephant and want to figure out what that thing is. So the first guy gets the tail and is like, oh, for me that looks like a rope with a brush at the end. The second guy goes to the side and he's like, yeah, I have no idea what you're talking about, but for me that's more like a rock. And then the third guy, touches the leg and he's like, I have no idea what you are feeling, but I see a tree here. So, and you get the picture. And this is how it goes, I think goes for us in astrobiology. So to really get an idea about what life in space is about, we are all blind in our separate fields. If I'm just an astrophysicist, I just look at one part of it, and if someone is a biologist, he or she looks at another part of it. So you really are like these blind men and the elephant when you want to understand this big question of life in space. And you all saw the aliens in the title, probably just came to hear about the aliens, so I'm going to give you some aliens, and I'm actually going to give you aliens that live on Earth already. First one, the blobfish. Was voted the ugliest animal on the Earth 2015 and 2016. Back-to-back ugliest animal in the Earth. Well, it's also a pretty cool animal because that blobfish has adapted to live super deep down in the ocean at pressures where even human-built things can even survive. So this ugly guy really knows how to live deep in the ocean, and this might actually be some sort of form of life we could find on these icy moons, these big ocean worlds outside in our solar system. Another one, the ice fish. So the ice fish has adapted to survive at temperatures of liquid water that is below freezing. So this guy can survive and even reproduce living in waters that are -degrees. On the other end of the scale, we have the Pompeii worm. That guy lives down at these hydrothermal vents, these underwater volcanoes, which with its feet in the hot and his head in the normal water. So just the gradient from his feet to his head is about 80 degrees. And he can even survive for short periods in water temperatures above 100 degrees, above the boiling point of water. And then we have this guy here, almost looks like an alien. And statistically, there should be 2 or 3 people in this room who have one of them inside of them. So I give you the homework to look up what it is, but that's an alien that lives inside of you. So these guys, we call them extremophiles. So things or organisms that love the extreme, that can survive in the extreme. And this is one lesson we learned from Life on Earth. It really develops into all of these niches and covers every form of life. And by studying these, and this is also part of astrobiology, studying these extreme environments, studying these extreme animals who live in these environments, because that gives us a hint, an idea about how life on other planets that have these environments could be like. And my favorite of these is the tardigrade. So it looks a little bit like a floating gummy bear or something. It's actually called the water bear. And this guy is just amazing. So if you can just, genetically engineer an astronaut, this is how it would look like. Sorry, but this is perfect. The second perfect astronaut here, but that is the perfect astronaut. So the cool thing about the tardigrade, as soon as it gets, if it loses its water, it puts itself in this cyst state. And in this cyst state, it can survive literally anything. So you can put it in liquid helium, in brine, you can put radiation on it, and it will just survive. And as soon as you put water back on it, like, Nescafe, it just comes off. So really, really great thing. So look up the tardigrade. It's not just cute, it's a really cool animal. But it's really, really survives, solar wind, anything. So this guy could really go for long travels in the solar system. Okay, but let's talk real aliens, right? You want to have real aliens. So I actually just got back, or like 6 weeks ago, I was at a so-called NASA Technosignature workshop in Houston, Texas. And Technosignatures means fingerprints of technological life that we may be able to detect from Earth. So one example, maybe some of you heard about these alien megastructures that some folks thought they detected. So at least technically, so these alien megastructures, long story short, turned out to be just like some crazy comets. But the bottom of the story here is we have the technology right now. So we have space telescopes like Kepler that should be able to see. No. We all have the same bingo cards actually. So you all have bingo at the same time. Good. So no one else has done it. So if you have bingo, you missed something. So we have the technology with Kepler to find if there were any super advanced civilizations that built these so-called Dyson spheres, basically just huge spheres of solar arrays around their stars to harvest all of the energy. So if there were civilizations out there, we right now have the telescopes to find that kind of stuff, and this is what some of the folks at the workshop were working on, and I have a few papers on one of these planets where we thought there might be, or one of these stars where we thought we might do something like that. Another little side project that I'm doing actually has to do with the moon. Yes. So we are looking for anomalies on the moon. And this picture here is actually, someone wants to take a guess which Apollo mission did this? The first image on the far side. Hey. So you paid attention last time. So this was one of the first pictures of the far side of the moon. So I got my obligatory Apollo 8 picture into my talk. So now I'm free to talk about everything. So what I do, or the little project I have, is we are using artificial intelligence. So there's a lunar orbiter called the LRO, the Lunar Reconnaissance Orbiter, which takes 130 terabytes of lunar surface data every year. So 130 terabytes is a shitload of data, and you can't get as many grad students to just look through the images. So you have to come up with something smarter. So our idea was to train a neural network, to train artificial intelligence on the Apollo landing sites. So you can see the images It's Apollo 11, 12, 14, 15, 16, 17. So there are actually imprints of the Apollo landers. You can see the landers, you can see even like the foot tracks of the astronauts. So our idea is to teach a machine learning algorithm to find these images in this huge haystack of other moon data. And then we might eventually find other things. So if this artificial intelligence is trained on finding the Apollo landing sites, what else is it going to find? So, want to make a guess? Anyone sees the anomaly in this image? There's something there. So what's that, aliens? No, it's just Russians. That was a Russian crashed lunar lander. One of the lunar, maybe, I'm not sure, but one of the lunar landers. So this is the stuff we may be able to find with this algorithm, and then, once we find these lunar landers, Apollo landers, this algorithm maybe shows us a couple of other images of stuff that we haven't seen before. So maybe we find the monolith or something, other crazy alien signatures on the moon. Anyone knows this quote, the book? The Hitchhiker's Guide of the Galaxy, right? So when I used to work at NASA, all my friends were like, yeah, come on, between the two of us, you can tell me, right, you've got like aliens in the barn and you talk to aliens all the time. And what I always answered them is like, how do you think that we could even talk to aliens? We cannot even talk to the next intelligent thing on this planet, like dolphins,
bingo,
or chimpanzees or bonobos. I mean, some people think they can talk to their dogs, fine. Anyone around here can think. But we can't really communicate with the next intelligent thing on this planet, which is made from the same DNA, breathes the same air, drinking the same water, and we can't communicate with them. So how would we even imagine to talk to something that might be made from silicon and breathes CO2, right? So how would that communication work? And this is actually also, some of you might have seen the movie Arrival, so this is really also a part of active research people at the SETI Institute who study animal communication. Or even now, really recent projects, they use two algorithms, basically two artificial intelligence that start talking to each other to figure out how we might eventually be able to talk also to alien civilizations. So this is really also part of this thing that I showed in the beginning. Even linguists are part of our astrobiology research. So no matter what you're studying, there's some sort of connection. We also have sociologists who look at what impact would it have on society if we find other life out there. So there's really a multidisciplinary, really truly multidisciplinary effort, this search for life in space. Okay, so what am I really doing? This was all, the cool stuff to get you interested. Now let's go to the boring stuff that I'm doing. So if you look up stock photos for astronomers, that's what we do, right? So in the morning I put on my white space lab suit with my tie, obviously. Then I put on my space security goggles. And then during the day I point my telescope to point somewhere, right? So this is what astronomers do, obviously. So what I'm studying are so-called exoplanets. Extrasolar planets. Planets around other stars than the Sun outside of our solar system. There are other stars that also do have planets. And as of today, I just looked that number up. We know about 3,870, about 4,000 of these exoplanets. So that sounds like it's easy, right? 4,000, that sounds like it's super easy to find them, but it's actually freaking hard. So to illustrate this is again real data taken by a solar observatory. So you might see this little dot here going through. Any guesses what that is? Mercury, exactly. So this is the transit of the planet Mercury. And that gives you an idea how hard it is for us to find these exoplanets. We look for these tiny little black dots next to these giant, super, blowing. Sometimes some of these activities are even more active than this tiny dot. So this is a challenge we have if we want to find these exoplanets around other stars. And usually we can't see them directly, right? There's no chance you see this tiny little dot next to the star. So what we need usually are indirect detection. So something happens with the star, or we get some data that lets us conclude there is some sort of exoplanet, some other planet that does this thing to the star. It might do very quickly. You should enjoy this slide. So we need indirect detection methods. And one of these methods is actually similar to what I just showed with Mercury. Because sometimes we are lucky enough, and some of these planets, some of these exoplanets also are within our line of sight. So their orbit is right along our line of sight, and then every time the planet passes around the star, it goes between us and the star, the light of the star goes down a little bit. And these are the observations that I'm mostly working on. So observing these reoccurring dips in the light curve, almost like a heartbeat. Every orbit, the light of the star goes a little bit down. And then from this, we can learn a lot about the planet. So first of all, we can learn the size of the planet. You can see if there's a small planet going in front of the star, you get a small dip. If there's a somewhat bigger Jupiter-sized planet going in front of the star, you get a bigger dip. So immediately you know roughly the size of the planet. What's even cooler is that when this planet passes in front of the star, some of the light of the star passes also through the atmosphere of that planet. And then we collect that light during this transit of the planet, we can also get signatures from the atmosphere. So in this phase, we can really feel out if there's oxygen, methane, CO2, water, or the trace atmosphere, even some trace elements in the atmosphere of these exoplanets. So this is the observations that I'm doing. And I'm doing them for the last 10 years. So I started as a young grad student. As astronomers, we always have to go to these ugly places like Hawaii and Chile. Here you can see me, younger me, around 10 years ago when I was observing at the two biggest telescopes, or the biggest optical telescopes on Earth, in Hawaii and Chile. And you also see that I was not busy enough with astronomy. I also invented the early form of dabbing at that point. And yeah, I tried that for a while, but it's really, really tough to do from the ground. So you can imagine if I want to study an atmosphere of another planet and look through the whole atmosphere of Earth, that doesn't make sense, right? This is like, you know, wearing pink sunglasses and distinguish two pink rabbits, right? This is really hard. So this is really why we need to get rid of the atmosphere. And one solution for this is, so one solution for that is actually crazy idea to put a telescope on a plane. Just like snakes on a plane, a telescope on a plane, and this thing exists. It's called Sophia. The Stratospheric Observatory for Infrared Astronomy also works in German actually. It's das Stratosphärenobservatorium für Infrarotastronomie. Scientists love acronyms. They love acronyms. They work in 2 languages. You can see here it's basically like a PIMP 747. And the garage door opens here, and then there's a telescope. And when I was a super young student, I dreamt of maybe one day working on Sophia, and you can see me 10 years later, I actually made it. So this is me in the cockpit of Sophia. This is us flying over Mars. You don't believe me? That's Mars. Yeah, this is how it looks when you're working, so you can see it's really different from the planes you know. Yeah, and I'm not going to talk too much about Sophia because maybe I'll come back next time and tell you more about why astronomers like to get high when they look for aliens. So this is my normal astronomy on Tap Talk. So maybe I come back and explain you a little bit more. Here also again you got me next to Sophia that you have a roughly idea about the scale. So it's the size of a plane roughly. Okay, so let's wrap that up. So the big future and the reason why I'm working in this field, and as we started with aliens and finding life in space, I really want to be part of the team that in this next 10, 20 years, and I'm sure with the next generation of telescopes, we have a chance to find so-called biomarkers, biosignatures, fingerprints of life in the atmosphere. So as I mentioned, you can look at the atmosphere of these planets when they move in front of the star. And then we can look for certain signatures, you know, if there's water, if there's methane, if there's oxygen, if there's some traces of life. And one of the best and most promising, if you trust the biologists, one of the best biomarkers is the combination of oxygen and methane. If you find oxygen and methane at the same time in a planetary atmosphere, that is a pretty smoking gun for life. And the explanation is, or some kind of analogy for that is it's like redstones and pizza. So if you put redstones and pizza in the same room, the pizza is gone in 5 to 10 minutes, right? The same happens if you put oxygen and methane in the same atmosphere. The oxygen and the methane react, and you shouldn't have both at the same time, just because they chemically recombine to something else. So if you find grad students with pizza at the same time, someone has just delivered, Papa John or Domino's has just delivered the pizza. So if you find oxygen and methane at the same time, something has just delivered the methane, which we think could only be life. So this is how this biosignature analogy with oxygen and methane work, but there are various other combination of molecules, so the general idea is that life takes something out of the equilibrium. So the atmosphere of a planet would be in equilibrium, but life takes it in disequilibrium. So we are looking for these disequilibrium, these outliers that not act as they're supposed to do. And the problem, however, is an atmosphere is not just the biosphere. So you got ices, you got oceans, you got volcanoes that interact. Maybe a volcano just spit out some pizza or methane. So it's really very many factors. There's photochemistry going up in the upper atmosphere. There are clouds. There's so many other things. Ocean circulation. So there's so many other things that give imprints into the atmosphere that we have to distinguish and make sure that there are no false positives for these biomarkers. And this is really one of these, so the atmosphere of a planet is really one of these elephants that I mentioned in the beginning. To really understand how an atmosphere of a planet works, we have to work together with geologists, have to work together with atmospheric chemists, need people who model the observation. So this is really a truly multidisciplinary effort. And with the next generation of telescopes, and this is what I'm really sure about, so if we get, maybe not James Webb Space Telescope, but the next generation telescopes that are built afterwards, we have the first shot, and for the first time in history, our generation has the first chance to find life out there in space. So this 3,000, 4,000 year old questions, are we alone? Are there planets or other stars that have life? We are the first generation in history that can answer this really biggest question in humankind, maybe. But we are also the generation that has to fix this planet. This planet's atmosphere is full of crap that others can probably observe and say that there's life. So we are the generation that might find life out there, but we are also the generation that has to take care of this planet, because that's the only one where we got beer. Thank you.
Thank you. I told you astrophysicists were cool. So, do you have any questions, guys?